Okay, I wanted to go over the packet that we worked on in class today. I know those were difficult problems. I know that when you saw the steps worked out, you understood them, but figuring out how to get one of those problems set up is not so easy. So for the first one, we were told, find the general form of the equation for all quadratics that have one x-intercept at the point 3, 0, and one y-intercept at y is equal to 0, 9. So in this case, because we were given one of the x-intercepts, we're going to use the factored form, which allows us to express that intercept right inside the equation. So the general setup that we're going to use for the equation is f of x is equal to some number a. We don't know what that is yet. In fact, there are going to be multiple values of a that would work. And so we're looking for a general solution to this equation. We know that one of our factors is going to be x minus 3 because one of our roots is x is equal to 3, and that's one of our x-intercepts here at 3, 0. Our other root is unknown to us, so we're going to call that q. So now we have the general setup for our equation. So the other thing that we know is that the y-intercept is at the point 0, 9. So what we want to do is take the form that we just set up, and we want to figure out how to express the y-intercept using that form. Because when we find the y-intercept from that form, we can set that expression equal to 9, and then we have an equation. So to do that, we take our equation and we set x is equal to 0, which is going to be true for our y-intercept. And we therefore get a times 0 minus 3 times 0 minus q, which is going to simplify to 3aq. What that means is that 3aq has to be equal to 9, and therefore aq has to be equal to 3. We're not going to be able to get any more specific than that. So what we have now is that the value of q is going to be equal to 3 over a, and therefore our equation now is f of x is equal to a times x minus 3 times x minus 3 over a, because we've replaced q with 3 over a. So what we see now is that when we look at our curve, as we change a, our curve always continues to pass through that y-intercept and that x-intercept. And the reason is that we set up the equation to have this value, f of x is equal to a times x minus 3 times x minus 3 over a. Therefore, all we have to do is change the value of a, and we get all the possible quadratics, if we were to run through all the possible values of a, that have these two points. This as the y-intercept, and this is one of the x-intercepts. Notice that when we get to a is equal to 0, we don't have anything at all because the function is undefined there. Because we have x minus 3 over a, we're dividing by a. If a is 0, the function is going to be undefined. But as soon as a is negative, we're again going to get a curve. Okay, so that's the first of our problems. The second of our problems we had was we were told that the vertex is at p0 and the y-intercept is at 0p. So because we're given the vertex, we are going to use the vertex form. And so what we know now is that we can set up an equation using the vertex form, and we can say that f of x is equal to a times x minus p squared, and p could be any value. And we could move p, and that would give us different quadratics. Okay, so we know again the y-intercept here, which is p. So we take our equation, we set x equal to 0 in order to figure out the y-intercept in this equation, and we end up with a minus p, and then that quantity squared, which is equal to ap squared. So therefore we can say that p is equal to a times p squared, because we knew that the y-intercept was p, and we also knew the y-intercept from this form was a times p squared. When we simplify, then we can say that a is equal to p over p squared. We divide both sides by p squared, or dividing through by p, we get a is equal to 1 over p. Notice again that we have something in the denominator, an unknown p, so p cannot have a value of 0. So now we have our equation. We say that a is going to be replaced by 1 over p, and then we have the rest of the equation, f of x is equal to 1 over p times x minus p squared. So in this case, we decided to express a in terms of p, and that way we can vary p, and the equation will modify itself as a result. So here we have our curve, and we can see that we have our equation. F of x is equal to 1 over 6.31 times x minus 6.31 squared, because currently our value of p is set to 6.31. So as we change p, our equation changes, and it always continues to have an x-intercept of p0, or a vertex of p0, and a y-intercept of 0p. Notice that, again, when we get p equal to 0, our function disappears. It's not defined. We have division by 0. But then when it becomes negative, we again have a situation where the x-intercept, or the x-vertex, and the y-intercept have the same values. Okay, so that was problem number 2. Problem number 3 was just a specific application of problem number 2, where we took p and we set it equal to 2. So when we do that, we get p is equal to 2 right here, and we have our equation. F of x is equal to 1/2 times x minus 2 squared. So when we solved 2, we actually also solved 3. Okay, so now let's take a look at number 4, where we were working with the directrix. And here what happened was we were told that we had a focus point at 2, 2, and a directrix at y equals 0. So again, the focus point is a point that will always be inside the parabola, and the directrix is the line that, for our purposes, will always be horizontal. Now, you could have a vertical or something that was oblique, and you could have a parabola, but it wouldn't necessarily be it would not be a function anymore, and so unless it was completely turned upside down. So we're going to be dealing only with the horizontal directrix line. Our vertex is halfway between the focus point and the directrix, and it has the same x value as the focus point. Therefore, we know that the vertex has to be at the point 2, 1. This should be 2, 1 here, because it must lie on the same vertical line as the focus point. We also know from our previous work that a is equal to 1 over 4p, and p is the distance from the vertex to the focus point, or in this case 1, because the distance from our vertex to our focus point is 1, and that's the same distance as the vertex to the directrix line. So we know therefore that a has to be equal to 1 over 4p, and therefore that a is equal to 1/4, because p is equal to 1. Well, now we have the vertex, we have the value of a, so we have our full equation, which is that f of x is equal to 1/4 times x minus 2 squared plus 1. Here's our vertex at 2, 1. Again, this should be 2, 1 up here, not 1, 2. And we have our focus point, we have our directrix, we have our value of a, in this case, must be equal to 1/4, or 0.25. Okay, let's take a look now at problem number 5, which was a calculator problem. You were asked to look at the situation where a shot put had a path that was described by the equation f of x is equal to negative 0.24 x squared plus x plus 5.5. And we'll change the rounding to 3 decimal places so we get our full equation here. And so here we have that exact quadratic. And we can see that we're really only interested in the portion that goes from x is equal to 0 to where the quadratic reaches a y value of 0. The x values here represent the horizontal distance the shot put has traveled in feet, and the y value represents the height of that shot put off the ground in feet at any given point in its trajectory. So in order to figure this out, we first wanted to know, well, how far did the shot put travel before hitting the ground? Well, that's just where the function has a value of 0. It's one of the roots. The other root is here, a negative root, but doesn't have any meaning in this particular situation. And we find that this root here has a value of, an x value of 46.586. So that's how far the shot put traveled before it hit the ground. We were then asked, what does the 5.5 represent? Well, that's the value of the function when x is equal to 0. So what it means in this case is how high off the ground was the shot put at time equals 0. So when it left the shot putter's hand, we're saying that the shot was 5.5 feet off the ground. So then we were asked, when does the shot reach its maximum height off the ground, and how high is it? Well, we find in our calculator, using the maximum function, we find that this point, which is the vertex and the maximum, has an x value of 20.833 and a y value of 15.917, which means that this 20.83 is how far it had traveled horizontally when it reached its maximum height, and that height was 15.92 feet off the ground. Finally, we were asked, suppose we wanted to figure out the interval during which the shot put was at least 7 feet off the ground. So what we did was we set our function here equal to 7. Then we subtracted 7 both sides to set it equal to 0, and we got a new function, and we found the zeros of that function. And what it turned out was that those had zeros of 1.558 and 40.108. So that meant that in this interval from x is equal to 1.558 to x is equal to 40.1, the height of this was at least 7 feet off the ground. So we can also see when we create the vertical line, or I'm sorry, the horizontal line, y is equal to 7, that right here, this intersection point is where it reaches a height of 7. We can see that's the exact x value that we calculated here, and that it drops below 7 feet right here at this x value of 40.108, which we had previously calculated. So you could either have found the zeros of the original function minus 7, or we could have found the intersection points of the original function and the line y is equal to 7.